All right, it's a new day. It's a new music selection. Today we're listening to Morphine. So by now you would have probably seen the video, hopefully for the Parabolic ATK1. I just left that title. And I believe you saw me go through the setup. Just do a quick recap here. This was the default Parabolic ATK. You guys should know where to get that. We get it directly from the toolkit. I chose to leave all of the default settings there, so I just wanted to make sure that we were able to get a solution, and that all worked out just fine. I then moved on to Parabolic ATK1, which was just a copy and paste, but I made a couple of changes to the parameters. If you remember, the way to change the parameters is to highlight the design we're interested in, and those variables will be exposed, and we can make the changes. I think I made the radius. I made this circular so it's minor and major are equal to each other. Maybe I changed the focal length. I can't remember exactly right now. I did an offset of 0. So this is starting to look a little bit more like the JPL antenna. And then I did another change, and I believe maybe this one, I deactivated the frequency sweeps. So these are off, which helped our solution speed up quite a bit because we didn't have to wait for the additional frequency sweeps. I believe so. We ended on this one, which was, it looks like the actual size of the Deep Space Network reflector. So 35 meters. I've got it in centimeters here. So make sure you do the conversion properly. And then we kind of estimated the focal length based on what you guys were doing in class. So we did all that. We got a result. If you remember, we were able to get the gain from either looking at the result plot. I'm just going to double click gain plot. We can see the maximum gain here was 64, it looks like. And then we can also get it from right clicking on the radiation far field setup by going to compute antenna parameters. So you guys should remember where to pull it out from here. Lots of other values we didn't really take the time to discuss, but look over that and ask questions next class. I'm going to close that out. So now what I wanted to do is I'm going to leave you with this archive design. If you remember, one of these, the last one took a very long time to solve. And there's a reason for that. And I'm not going to get into the details in this video. We can maybe discuss it in class. But what I did instead was I'm using two new antennas. Let me just minimize this. So Howard and Kivrin both sent me different versions of reflectors. Kivrin, I believe, sent the HFSS model, the electronics desktop model, and Howard sent just a bare CAD model, a step file of a reflector. So what I wanted to do was show how I'm able to speed up the solution again, also using hybrid simulation, but I changed the way that we're doing it. So I want to walk through that process real quick, and that's what I'm going to do. So anybody who's interested, especially Howard and Kivrin, you're kind of taking the lead on these reflector antenna designs. So I highly recommend you pay attention to this section, and I want to encourage you to try to optimize your designs to try to hit our targets. So first, what are those targets? So we're going to go to the JPL document, and this is the one that I believe Howard has been referencing quite a bit. I just searched for DBI, and it brings me right over here to the 34 and 70 meter antenna. So we're going to be focusing on the 70 meter. We're trying to find the one that will give us the maximum gain in X band. So here I've got two references for DBI for gain. I've got the 70 millimeter uplink, and the X band value is right here. So I've got a slightly different value for the uplink of the 70 meter reflector compared to the downlink. So if you just, they're pretty close. One's a little bit higher. So let's just say a reasonable number for the target of that gain is going to be, let's just say 74 dBi. So that's our goal. We're trying to replicate a reflector antenna with our HFSS design that gets us about 74 dBi specifically. So I went ahead and solved these values already. So I want to explain the process a little bit about how I did this. So I'll get to both of these designs in a second. I started with the feed horn. So it's very important that you recognize the terms that are in parentheses here. These are the solution types. So it's not a design type. They're all HFSS design types, but there are different solution types. And the way that we select those is by going into this menu, and I choose solution type, and you can see this antenna is called what you're reading right here. The other two, you'll see we selected SBR plus design types. We didn't do that in class. We didn't do that in the video that I set up yesterday, where we solved an SBR plus region, different than a solution type, and I'll show you what the primary benefit was of doing that. So the first thing is that this horn might look familiar. We went over this in class. All I did was take one of the designs from the parabolic ATK1, and I literally copied it and pasted it, and I deleted the reflector. I did that in class, if you guys remember. So everything should be set up the same from whichever one I copied it from. So these frequency sweeps are disabled because I did that before. I still have these radiation patterns were set up. I have a far field result here. I can look at that. You guys remember we discussed this in class a little bit. This is a far field pattern from the feed antenna only. If I right click on the result node, I can say it's show in modeler view. It's toggled on, and if I want to see it, I can just double click, and that's what it looks like. So that's the energy representation in a gain pattern form coming from the horn antenna. And if you remember, the idea was use this feed horn to illuminate the reflector antenna and let the parabola do its job to focus the energy and give us even a higher gain. So I can get a gain value out of this one by going to the radiation sphere. I'll choose ATK 3D again, and I'll compute antenna patterns, and I can see it here. So I can go with just peak gain value. So remember, that's a linear result. If you want the true gain in dBi, you'd have to multiply 10 times the log of that number. Okay, and that's how you get it in dBi. So you'll find out that that number is significantly lower than what we see with the reflector. The other way to see the gain, if you go back to here, the peak gain is usually identified. For some reason it's not. For some reason it's not being shown. I expected the peak gain to be identified on this plot, but I can see up here the max is 13.15. So that's in dB scale, which makes sense. If you do the conversion, the linear in your head, it's roughly going to be about 13 dB. So this all looks good. So now I have a feed horn, and what I want to do now is bring in the other objects. So I did this two ways, I believe. I probably, if I'm remembering correctly, let's just start with Howard's design. What I did with Howard's is Howard sent me a step file, and you can see here this is the name. I believe it was probably done in Fusion 360 is my guess. You can see I assigned it a peak material. That's one of the first things that I did. And then you can see I did some operations here. I wanted to orient this properly. So I did a move operation on it, and then I did a rotate operation on it. So you can see the parameter values for what I did. If you wanted to reproduce that, you can just edit, you can delete these and use these numbers. Same basic idea. So the step file that we imported, the way that you import that is you come up to HF Modeler, and you go to import, and then it's just going to ask you for where the file is, and you can see mine's right here. It's a step file. Okay, so that's the way you do that. Once the object comes in, I applied it. I applied the material. It's a solid object. If it was a surface, I would not be able to give it a material. I would have to do it differently, and I'll talk about that with Kivern's design. Hopefully, I don't forget. Okay, so I made some decisions on how to orient it. If I zoom in here, of course I want my feed horn to be pointed directly at it, so that looks good. And then I had made some decisions about how far to separate it based on the proper focal length, and I didn't do any calculations. I just did a rough estimate. So here's kind of the magic of what happened, to be able to get this to solve fast, because this whole thing did not take a very long time to solve. If I go to results, I'm in Howard's design here. I go to solution data. If I go to the profile, this whole thing only took me 23 minutes to solve. Compare that to 5 hours that it took to solve the very last design from the previous video. So quite a difference. So let me show you how I did this. I'm going to go ahead and copy this design. It's already solved. I don't want to lose this result. So I'm going to go to paste here. So I'm going to call this demo, so you guys can see exactly how I do it. And what I'm going to do is remove this link. So I went into 3D components, and I'm just deleting that feed horn. So now, if I go into zoom into 0, 0, 0, I can see there's actually nothing there. So the key is that this feed horn is still in the project called Parabolic Custom, but I've deleted it from this design called Demo. So now I'm gonna do something called a link. So it's a little different than when we did hybrid regions, because remember, I'm in an SBR plus design type, and that's why the process is a little bit different. So here's what I'm gonna do. I'm gonna right click on 3D components. Instead of browsing, I'm still gonna create antenna, but now I'm gonna do it by selecting link to source design. And when I do that, the real trick is that I'm letting it choose far field type instead of near field. So in the last solution that took 5 hours, we ran it from near fields. And I had mentioned in class the ability to take fields that are captured on the perimeter of the object and use those. There's another way of doing it where I'm really reducing the amount of information that I'm using to illuminate that reflector, and I'm using something called a far field. We haven't talked too much about that, but let's just say the gain patterns that you're looking at is basically the far field. And in this case, it's an acceptable approach to use a far field type for this feed horn because of the location and the size of that reflector. So I'm going to leave that on. This is the number one thing for you to get a fast solution here. And now I go to set up the link, and when I set up the link, I have to go find that source object. Well, that source is actually in this project. I can see it right there called feed horn. And when I toggle on use this project, it's trying to search for valid objects that I can use. So I'm going to use this. The source design is the right one. It's the only option that it's giving me right now. Instead of doing a sweep, I'm going to use the last adaptive pass. If you remember that, that's our converged solution, and I'm going to select that. And sometimes I toggle this on in case it hasn't been solved yet. It'll solve the feed horn before it goes on to the linked solution with the reflector. Okay, so with that, I'm going to move on to, I'm not going to worry about variable mapping right now. I guess that could come in handy. So actually, there's nothing to change right now on this. Don't worry about model blockage and model visualization. You'll see what this does. I'm going to go ahead and toggle on the waveguide outer, and that's probably all I need. I'm just going to do that right now. I'll leave everything off. This is referring to structure objects from the source design, the feed horn itself. So I'm only going to see what's identified as WG outer, waveguide outer. So when I OK it, I'm gonna hit next, and then if you watch what happens when I say finish, now right where I expected it to be is an image of that source object, the horn. Different than bringing the object directly into the design, so it's doing a link. So it's going to go pull the information from that solution and use a far field representation to illuminate that horn. So another thing I can do is when I choose the object, I'm going to save as I go here. When I go into the 3D components in 10.01.1 object right there, I can see some information here. If I go to visualization, I can show the pattern. So I can turn on show pattern, and that's what it looks like. And I can do, sorry, I just lost my view. I'm going to choose fit selected. I should be able to get it back. And if I hold control, I can, oh boy. I must be behind the reflector, I think. And there we go. So let me zoom in now. So this pattern basically is going to be used to illuminate that reflector. And that's all the difference in the world when it comes to the speed of the solution. So if you can remember how to set up that link, I just kind of did it from scratch. I'm not going to go through the rest of the setup. I cheated by copying and pasting. I encourage you to go ahead and do that. We've got lots of models that we've been sharing with each other, so feel free to do that. Okay, so that's how I set up the link. When I went ahead and did the solve, let's just verify that I've got everything good on the demo. So if I validate, this is telling me that I do actually have a valid solution. I already solved these, so let's go. That demo was for Howard's design. Just so I don't confuse anything, I'm going to go ahead and delete it. And now I have the solved version of this. Exactly the same thing that I just described was already done here. So if I go to this gain plot, I can see the thing that's solved in 23 minutes or so. It's getting me a pretty high gain. Now this pattern, again, it looks very jagged. And the reason is because the sampling sphere that I gave it to project this pattern on is pretty sparse. It's not really dense enough, so it's not giving me a very good graphical image. In reality, though, I believe the data should be there without us having to worry about changing this, the settings of that sphere. So we can see if we want to get the exact value, I can go to Infinite Sphere, right-click, Compute Antenna Pattern, and here's a value for peak gain, so we can use that. So just try to remember roughly 41,000, and that's linear. So you got to remember to convert that 10 log of that number is what you're going to get in dBi. Kivrin's design, Kivrin gave me a HFSS design that was already ready in Electronics Desktop. So this is a parameterized version that we've been getting from Antenna Toolkit. These are the numbers that I see. It looks like your major and minor radius are 7 meters each, equally. Your focal length was about 5 meters. So this looks good. You'll notice that there's no. I went ahead and did the link the same way for Kivrin's design. So just what I demoed for Howard's design, I went ahead and did the exact same thing. I just don't have the pattern exposed. I don't think so. But we went ahead and solved this as well. This has even a higher gain. Actually, it's not a higher gain. Is it a higher gain? So let's go see. We'll go to compute the antenna parameters here, and it is a higher gain. So this value is much higher. I went ahead and put these in the calculator earlier. So try to remember this peak gain of 770,000-ish. I should have them in here. So this should be Kivrin's. I did log of that number that we see times 10 is giving us a gain of about 59 dBi. I did the same thing for Howard's design based on everything that I set up for the location of that reflector, and I'm getting a gain of about 46 dBi. So 10 log of that number, the linear number. So if we compare that to the target that we looked at earlier, where are we? Well, we're in the ballpark, but we're sort of getting in the ballpark, but both of these are falling short of that target that we know we should be able to get from this specification. So I guess my challenge for you now is to see if you can take your respective designs or with the limited time that we have, maybe you guys settle on one of these designs and see if you can tweak it to get to get to get something closer to this 74 dBi number that we see here for the X-band. So I'm going to leave you in the final segment here with a couple of tips and maybe some ideas of how you might go about doing that. So I'm going to use Kivrin's because one thing is that it's even faster than Howard's solution. There's a couple of reasons. One is because the reflector is smaller, which, by the way, I recommend making it larger. This doesn't meet the number, but it, right, 7 meters radius is going to be 14 meters diameter. So it's not quite our 74 meters, right? So, but that's okay. I think you start small because the solution is going to be a lot faster. And if things start to make sense, then you can look at a larger size antenna. So one thought is that maybe the location of the feed, if you could specifically determine the focal length, that's ideal, and place the feed in the appropriate location. I believe it should be directly at the focal length, but I'd have to read up on that. To be quite honest, with an X-band feed, things could be a little bit different for an optimal performance, but I think that's worth trying. And one way you can do that is, first of all, I did want to comment on why it is so much faster, in addition to the size. Notice that Kivrin's model, this is actually a surface. It tells us it's a sheet, and forget the equations of how it was generated. That was all done for us when we set it up with Antenna Toolkit a while back. But think of it this way: Howard's design was a thick, it was a solid. It had a thickness to it. So the meshing that would be done would actually be done on equivalent mesh on both sides. In addition to the thickness, I think that's one reason why it takes a little bit longer. Also, the fact that it was a larger size. But when you model a sheet surface, you'll recognize that we can't assign a material to a sheet. But what you can do is put a boundary on it. So in this example, if you're going to use a sheet geometry, if I select the object and I right-click, the way that you do that is through assign boundary, and that was also done for us. And this was given a perfect electric inductor boundary. So I'm not going to do it again. It's already set up. I can see it right here. So when I choose it, it tells me. Okay, the other thing is if I look at the antenna here, when I did the link, I must have forgotten to turn on geometry. So I only see the bounding box. But if I click on that antenna, just like in Howard's design, I should be able to show the pattern. So I know that something's in there, and that looks identical to what we saw with the demo model that I put together. I can see that antenna pattern and some back lobes. The scale's a little bit different, but I know that I have a good design. So one thought here is play around with the radius of the antenna. I'm going to go ahead and copy this design so I don't mess up what I want to send you guys. And I'm going to make a couple changes here. Let's go ahead and go with, let's say, 1,000 centimeters, or 10, wait, 1,000, yeah, that's right. So that would be 10 meters, and then 1,000 centimeters here. So I've got a larger reflector now. This focal length is changing the shape of the actual reflector itself. If I go to let's just see what happens when I bring that number down. That's less like the shape that I'm looking for. If I bring it up, then that's a little bit broader of a shape, so it's going to push my focal length out a little bit. So the focal length is not connected to the location of the horn. So if I look at the feed location, I ought to be able to see it move when I change the feed location. So let's just try, let's say -100. And that's not changing anything. So I must have broken the parameterization for this. I'm going to pause while I try to figure this out. So I think when I copied and pasted and changed it to an SBR Plus design, the feed horn is no longer part of the solution, or I should say the design. The structure is not. Doing the link changed the way that that structure is going to be controlled by my parameter. So I believe that I just kind of killed that by copying it into this design type. So what I'm going to do is make an equivalent. If I come in to the modeler tree and I select antenna 1, I believe I can set up a move parameter now. So what I'm going to do is, before I do this, let me just verify. Feed location is a variable that already exists. So I'm going to go ahead and reuse that variable, and I'm going to assign it an operation here. So pay attention. I've got feed underscore location. That's the thing that I want to use. I select antenna 1, and then now I'm going to move, and I'm going to zoom in. And if you remember how this works, one way to do this is that I can let's just choose the center face. You see when it turns to a circle there, that kind of helps. It asks me on the bottom left, input the reference point for the move vector. Well, that's my reference point. Now I'm going to hold the Y key down so it limits me to the axis. So I think on the server, I hope this works for you guys. The 3-button mouse would really be helpful here, but hopefully you can do this. And I'm just going to bring it in a direction, and I'm going to click the left button when I'm done. Excuse me. And that I can see now I've got that operation here. Instead of the value, I can't remember the parameter now. Feed location. I'm gonna cancel that. Feed underscore location. So when I go to move, click back here. Instead of this value, I'm gonna call this. Notice that's X, comma, Y, comma, Z. I'm replacing the Y with literally feed underscore location because this is a parameter. It sees it. I'm going to select it, and I'm going to, let's see if it moved back. So I should be able to see, whoops. Okay, there we go. I should see that it's in the original location now. Now, if I change this, let's say to 100, it just moved away. So here's my origin, and now it went in the positive Y direction. I made feed location 100. So this is nice because now I've got it tied back to a variable here. So if I said -10, I should see it move that way. If I said -20. So now what you can see is I'm kind of gearing up to do, we talked about these parametric solutions. So let's define one right now. So I'm going to go ahead and save this. And I'm going to go into the model. I'm going to go into the project tree, and now I want you to look at this thing called optometrics. So lots of steps in this process as well, so you got to be very careful to follow this also. So I'm going to right click, and I'm going to add, and I'm going to choose parametric. So when you choose parametric, a window should show up with all these tabs. We're going to go through some of them, but not all of them. The first thing I want to do is set up the sweep definition. This is not a frequency sweep, this is a parametric sweep. So I'm going to say add. When I add, I can see there's a number of things that I could change, which you might think about later, but for now we're going to keep the major radius and the minor radius and the focal length what we set, and I'm going to only parameterize feed location. When I do that, it's giving me some default values here. So let's just say I'm going to go with a few. I'm just going to say -100 centimeters is 1 meter. So in the closer to the reflector direction, and then I'm going to go farther. I'm going to go 100 centimeters, and I'm going to do them in steps of 50 centimeters. I'm not done until I say add. When I add, it's going to show up here, and I'm just going to OK this for now, and let's verify it's a nice little helpful tool to go to the table and see if this makes sense. So this, we already have a 0 centimeter case, but now we're going to add 4 more to it. So this is the sweep it's going to run. So that's exactly what I thought I would see. Obviously, the more points you run, the longer it's going to be. It's got to resolve. So now, if I go into, I think general is going to be okay. Notice this is very important that you're pointing to a simulation setup. It's talking about this guy. Well, it won't let me see it right now, but when you open up analysis, you're gonna see this setup 1. That's the simulation setup that we want. It's the only one that we have. I'm gonna leave these values alone for now. Nothing to do with calculations. This is probably, I'm gonna turn both of these on. And I'm not gonna get into the details of why I'm doing that. For an SBR solution, I believe I have to do this to get far field patterns. So that's what I want. I want to get far field patterns for each of these. So, okay. So with that, I think I'm all ready to go. We should be good. I'm going to say okay, and I'm going to save this. And then now, before you run, let's just make sure this actually looks like something we want to look. It looks like what we expect. One little trick you can do is I can right click on parametric setup and I can go to animate. And when I animate, I'm going to choose, you probably get an option for radiation pattern. Choose that and say okay and say animate. And is it doing what we think it should be doing? It's moving along the Y. So every parametric run is going to give us a different feed location that we see here. And it's going to store these results so we can plot them. Or I should say, even better, we can calculate what the gain is going to be. So let's do that. I'm just going to right-click parametric setup, and I'm going to validate. Looks like it looks like it's running. I don't think it actually ran though. I'm going to go ahead and hit analyze now. So you should see, there we go. So it validated, it looked like it was running, but it actually validated, and then it's going through the solution. So you can see how fast this is moving. Compare this to the thing that we did earlier with the near field instead of the far field link. Would never be able to do a parametric run like this. I'm gonna let this go, and I'll show you how to evaluate the 4 or 5 different positions here on parametric, check the gain, and then you're kind of off to the races. You can set up your own parametric run. Howard, you can do the same thing with that reflector, if your step file, if you decide to use that. So I would recommend you guys work together and probably choose one common model to do your perturbations on. You can sweep any parameters that you want that are defined in there. So this is almost done with the first sweep, so this is going to be pretty quick. I'll come back and we'll look at the results as soon as it's done solving. All right, I'm gonna say, I guess I already saved. So I've got a completed result. If you look down here in the message manager, this didn't take long at all. It's the wrong one. It's Kieran 1. You can see the feedback here. It's telling me that it started all these various solves here. It even gives you an update, I believe, on the. Let's see. I'm just going to read this a little bit closer here. You can see right here the variation. So this is calling out feed location 50 centimeters. I should see that repeated as it moves. Here's the feed location 100 centimeters. So you should be able to verify that everything in your parametric sweep is going to be there, and it should show up with with a successful solution. So let's look at the radiation pattern. I'm going to go into results here. And let's double click gain plot, and let's see if I can get this to work. I'm gonna right click in the dead spot here and say modify report, and I'm gonna go to families and choose. So real quick, just want to make sure you're following along. These tabs up here, we have trace and we have families. Everything here looks good. The category of gain, gain total, and dB, we like that. but we want to choose specific values from our suite. So one of the variables is frequency. We haven't messed with that. That's been 10 gigahertz the whole time. But notice feed location nominal is being shown here. If I click into the ellipsis, I can choose specific values. So let's just start with the negative 100 centimeters. That's 1 meter closer to the reflector. There's nothing to do after I select it, except I can hit apply trace, and I believe it's gonna. I hope it updates for me, and it sure did. So I can see my peak gain here. So that looks like 36 dBi for that one. So now I'm going to change it to negative 50 and see if that value has changed. And again, I can just kill that box and I'll apply trace, or I could do a new report. I'm just going to try to remember what that value was. So 36 dBi, you could write that down, and I'll say apply the trace, and I should see it regenerate, hopefully. Changed. Try a different value. I don't remember doing negative 20. It must have been one of my previous settings. Let's go to 0. Apply trace. That was an update. Certainly an update there. I've got 61.7. I'll go do it again for this position, 50 centimeters, and I'll say apply trace. And now it's come down dramatically. So the gain, it's interesting because it looks like possibly the feed might be working better, but the gain has actually come down. It could make sense. So let's look at the final value here and apply that trace. Changed again. So you can resolve this quite a bit, and I'm just giving you one idea for exploring different ways to see if we can match those target gains. So obviously, let's go ahead and change to a larger reflector, maybe replace this with Howard's step file. Maybe you could tweak that design a little bit and really understand the focal length and where that feed should be. Place the feed at the focal length before you import it, or after you import it, orient however you need. So play around with these values, and I guess my challenge for you guys is to see if you can just tweak this along now that you know how to improve the solution, and see if you can get something close to the Deep Space Network antenna, and for a gain value. And yeah, hopefully this helps. I'll see you guys back in class next week, and good luck to you.